For billions of years, Earth was lifeless, but deep in its ancient oceans, something extraordinary began, the first spark of life. Over 3.5 billion years ago, single-celled organisms emerged, and after eons, the first true animals appeared, strange pioneers that would become the ancestors of all creatures, including us. Our journey starts in the Ediacaran period, 558 million years ago, with Dickinsonia, a creature that looks like a quilted pancake pressed into ancient seabeds. Dickinsonia's fossils, found in Russia and Australia, range from tiny to over a metre long. For years, its identity was a mystery. Fungus, lichen, or animal? The discovery of cholesterol in its remains finally proved it was one of the earliest animals. Dickinsonia had no mouth, gut, or anus. It absorbed nutrients directly through its flat body, lying on microbial mats and digesting food externally. This simple feeding method was perfect for the nutrient-rich Ediacaran seas. Dickinsonia's large, flat shape maximized absorption, allowing it to thrive. Its existence shows that early animals could be large and complex, not just tiny worms or sponges. Dickinsonia marks a crucial step in evolution, a time before predators, when life was slow and gentle. Its discovery pushed back the timeline for complex animal life and revealed a world utterly alien to ours. Dickinsonia is a testament to evolution's creativity, a pioneer paving the way for all animals to come. It reminds us that the path to modern life was filled with strange, wonderful experiments. Dickinsonia's quiet success set the stage for the explosion of animal diversity that followed. Next, we meet the sponges, ancient animals from the phylum Porifera, dating back at least 600 million years. Sponges have no brain, nerves, or muscles. They're colonies of specialized cells forming a network of canals and chambers. Their bodies draw in water, filtering out bacteria and plankton for food. Conocytes, or collar cells, use tiny flagella to create currents, trapping food as water flows through. This filter-feeding strategy has kept sponges thriving for hundreds of millions of years. Sponges are living fossils, showing how multicellular life can succeed without complexity. They play a vital role in ecosystems, cleaning oceans and providing habitats for countless creatures. Their simple design is a powerful evolutionary advantage, enduring through mass extinctions. Studying sponges reveals the first steps toward multicellularity, how cells cooperate to form larger organisms. They mark the transition from single-celled life to the complex bodies that would follow. Sponges are our most distant animal relatives, humble yet foundational. Their story is the beginning of animal life as we know it. For the pinnacle of simplicity, meet Trichoplax adherens, a tiny, flat, nearly invisible blob discovered in a saltwater aquarium. Trichoplax is just a few thousand cells with no organs, muscles or nerves, only 3 cell layers. It glides over surfaces using cilia, constantly changing shape as it hunts for food. When it finds a meal, it secretes enzymes to digest food externally, then absorbs the nutrients. Despite its simple body, Trichoplax's genome contains genes for complex structures found in other animals. It holds the genetic toolkit for complexity but doesn't use it, making it a living blueprint for animal evolution. Trichoplax may represent a living link between single-celled ancestors and the first multicellular animals. It shows how cells first clumped together and specialized before true tissues and organs evolved. This creature challenges our definition of an animal, reminding us that complexity isn't always visible. Trichoplax is a window into the dawn of animal cooperation. Its simplicity hides the secrets of one of life's greatest transitions. In its humble form, we glimpse the origins of multicellular life. Now, we meet the cnidarians, jellyfish, sea anemones and corals, among the first animals with true tissues, nerves and muscles. Their nerve net, a simple web of nerve cells, lets them sense and respond to their environment. Cnidarians can move with purpose, pulsing through water or anchoring to rocks. This movement opened new possibilities. They became Earth's first predators. Their stinging cells, called cnidocytes, fire venomous harpoons to capture prey. With radial symmetry, their bodies respond to stimuli from any direction, ideal for floating or stationary life. They have a single opening for eating and waste, leading to a simple digestive cavity. The rise of cnidarians changed evolution, introducing predation and driving defensive adaptations in other animals. Their nerve net was the ancestor of all nervous systems, the first step towards complex brains. Cnidarians' innovations shaped the future of animal life. They show how simple changes can spark evolutionary revolutions. The first movers and shakers, they set the stage for the animal kingdom's next great leaps. Their legacy pulses through every nervous system on Earth. Our final subject, Otavia antiqua, may push animal origins back to 760 million years ago, deep into the cryogenian snowball Earth era. Otavia's tiny hollow fossils found in Namibia resemble miniature sponges. If confirmed as animals, they would show that life survived even the harshest global ice ages. Otavia's structure suggests it filtered food from water, much like modern sponges. Its discovery has sparked debate. Are these true animals or something else? If Otavia is an animal, it means the genetic toolkit for animal life existed long before the Cambrian explosion. It would be the ultimate survivor, enduring one of Earth's most extreme climates. Whether animal or not, Otavia challenges our ideas about when and where animals first evolved. It reminds us that the story of life is still being written, with new chapters waiting in ancient rocks. Otavia represents the frontier of paleontology, a tiny fossil that could rewrite our origins. The search for our oldest ancestors continues, pushing us to explore deeper and further back in time. From Dickinsonia to Otavia, these early animals were the first drafts of life's story. Their experiments in movement, feeding and survival laid the foundation for all animal diversity. Studying them reveals how simple beginnings led to complex life, including us. Their legacy lives on in every nerve, muscle and cell of modern animals. They connect us to a vast ancient family stretching back hundreds of millions of years. The story of the first animals is ultimately the